Have you ever stopped to think about the sheer magic of something like ChatGPT? You type a question, a half-baked idea, a silly request for a poem about pizza, and out comes this coherent, often brilliant piece of text. It feels like talking to the future. But what if I told you that the engine behind this magic isn't an unknowable alien technology? What if I told you it's something that we as developers, as curious minds, can actually understand, build, and even hold in our hands? Metaphorically speaking, what if you could build a large language model from scratch? Welcome to Beep Beep Pop Poop podcast. That's the new name. I am your host, Baris. Obviously, my name is not Baris. My name is Baris. Sorry, I was just made a mistake while reading the text. A full stack developer living here in Poland, usually swimming in the world of TypeScript, but today we are diving headfirst into the Python-powered universe of AI. I recently got my hands on a book that felt like it was written just for people like me. People who aren't just content with using the tools, but who have this burning desire to look under the hood, take the engine apart, and understand how it truly works. The book is Build a Large Language Model from Scratch by Sebastian Raschka. I hope I pronounced the name correctly. And that's exactly what we are going to do for the next 19 minutes. I don't know actually how long it will take. Something around that. This isn't just a book review. This is a deep dive. We are going to unpack the core ideas piece by piece, from turning simple words into numbers to the very mechanism that allows a model to pay attention, and finally to how it all comes together to generate text. By the end of this, you will not only understand the concept in this book, but you will see the entire landscape of modern AI in a completely new light. So grab your coffee, get comfortable, and let's build an LLM. Intro. Okay, let's pass the intro. Before we start coding in our minds, let's set the stage. Who is Sebastian Raschka? And why did he write this book? Raschka isn't just some academic theorist. The book makes it clear he is someone who has been deeply immersed in the world of deep learning, coding LLMs for years. He has a popular blog and a knack for explaining complex concepts from the ground up, which is a rare and valuable skill. This book feels like the culmination of the passion, a desire to demystify one of the most transformative technologies of our times. The book was published in 2024, at a time when models like GPT-3 and ChatGPT have already changed the world. But for most of us, they remain black boxes. We interact with them through an API, but we don't understand their soul. The core problem Raschka is tackling is this: how can you truly understand, customize, or even recognize the limitations of an LLM if you have never built one? Traditional approaches might just show you how you use a library like Hugging Face. Raschka's approach is different. He says, let's throw out the high-level libraries for a moment and build this thing primarily using PyTorch, a foundational deep learning framework. It's an educational journey designed to give you a first principles understanding. So, what is the book's central thesis? It's simple but powerful. The best and perhaps only way to truly grasp how large language models work is to build one yourself from scratch. It's an argument for learning by doing, on the most fundamental level. Think about it like this: you can learn about cars by reading manuals and watching videos. You will know what a carburetor is, what a transmission does, but imagine you actually built a car engine from individual components. You would understand the relationship between the pistons, the crankshaft, the valves, in a way you never could before. You would feel the logic of it. That is what Raschka proposes for LLMs. He argues that by coding the entire pipeline from loading data to final fine-tuning, you gain an intuition that is impossible to get otherwise. Another way to look at it is through my world of web development. I can use a framework like Next.js to build a complex web application quickly. It's powerful but hides a lot of complexity. To become a truly great developer, I need to understand the underlying technologies: React, Node.js, how HTTP requests work. This book is the equivalent of that for AI. It argues that while using off-the-shelf models is useful, building one reveals the why behind the what. It shows you why an LLM is structured the way it is, what its limitations are, and how you could begin to customize it for your own specific needs, like creating a model specialized for finance or medicine, which the book notes can outperform general models. Alright, let's continue. Now let's get into the core of the book. This is our deep dive into the key components of an LLM. We will walk through the main stages just as the author lays them out. Our first step, and perhaps the most fundamental challenge, is working with text data. How do you take a sentence like "every effort moves you" and turn it into something a computer, which only understands numbers, can process? This is a topic of chapter 2. And the answer is a two-step process: tokenization and embedding. First, tokenization. At its simplest, you could just split the sentence into a list of words and punctuations. Every effort moves you can actually be separated word by word. Every effort moves you. The book walks us through this simple approach first. But what happens when you encounter a word the model has never seen before, like a typo or a new slang term? The simple tokenizer would fail. This is where a more clever technique used by models like GPT comes in: Byte-Pair encoding, or BPE. Think of Byte-Pair encoding as a smart compressor for language. It starts with a vocabulary of individual characters. Then it iteratively finds the most frequently occurring pair of characters and merges them into a single new token. For example, E and R might merge to R. Then T and H might merge to T. Then T and E might merge to D. T-H-E, D. This process continues, building up sub-word units. The magic of BPE, Byte-Pair encoding, is that it can represent any word. If it sees an unknown word like Akwirv, A-K-W-I-R-W, it just breaks it down to sub-word tokens it knows, like AKW. This means the model never encounters a truly unknown word, which is a brilliant solution to a huge problem. Once we have these tokens, we need to turn them into vectors, or embeddings. An embedding is just a list of numbers that represents the token. For GPT-2, each token is turned into a 768-dimensional vector. But there is a problem. The word moves will have the same embedding to vector no matter where it appears in a sentence. But its meaning changes with position. To solve this, GPT models use positional embeddings. It's a simple, brilliant trick. For each position in the sequence, first, second, third, there is a unique vector. This positional vector is added to the token embedding vector. So the final input for the model is a combination of what the token is and where it is. That's really important because that separates normal tokens from positional tokens. After all, meaning of a sentence may change as tokens or the words change. Okay, our text is now a sequence of vectors. The next key concept, and honestly the very heart of the transformer architecture, is the attention mechanism, which the book dedicates all of chapter 3 to. Before transformers, models like recurrent neural networks tried to process language sequentially, compressing the meaning of an entire sentence into a single state vector. This was like trying to remember a whole paragraph to summarize it later. You would inevitably forget early details. Attention changed everything. The core idea, as described in the famous paper, "Attention is all you need," is that as the model processes a word, it should be able to look back at all the other words in the input and decide which ones are most important for understanding the current word. The book explains this beautifully by building it up from a simple version. In the self-attention mechanism, for each input token, we create 3 vectors: a query, a key, and a value. Here's my analogy. Imagine you're at a crowded party, the input sentence. You are the query vector. You want to find out some information. Every other person at the party has a name tag, which is their key vector. To get information, you compare your query to everyone else's key. If there is a strong match, a high .product score, it means that person is very relevant to you. You then listen to what that person has to say. That's their value vector. The final context you get is a weighted average of all the values, where the weights are determined by how well your query matched each key. This allows the model to create a new context-rich representation for every single token, based on all other tokens. For a text-generating model like GPT, there is a crucial twist: causal attention. When predicting the next word, the model should only be allowed to talk at the word that came before it. It can't cheat by looking into the future. Causal attention implements this by applying a mask to the attention scores, effectively hiding all future tokens from the model's view during the calculation. The final evolution of this is multi-head attention. Instead of having just one set of query key and value weights, the model has multiple heads. The small GPT-2 model has 12. Each head performs the attention calculation independently, with its own set of weights. It's like having 12 different people at the party, each listening for different kinds of information. One head might focus on grammatical relationship, another on semantic similarity. The output of all these heads are then combined, giving the model a much richer, multifaceted understanding of the input sequence. Now we have our building blocks. The next step is to assemble them into a transformer block. The focus of Chapter 4. A transformer block is the fundamental repeatable unit of a GPT model. It's like a Lego brick that you stack to build the entire structure. A single block consists of two main parts. First, the masked multi-head attention module we just discussed. Second, a simple feed-forward neural network. These two components are wrapped in what are called shortcut connections and layer normalization. Shortcut connections are brilliant. They allow the input of the block to be added directly to its output, creating a direct path for information and gradients to flow, which makes training very deep networks possible. Layer normalization keeps the numbers from getting too big or too small, stabilizing the whole process. A GPT model is then simply a stack of these transformer blocks. The small GPT-2 model we are exploring stacks 12 of them on top of each other. The input embeddings go into the first block. The output of that final block goes into the second, and so on 12 times. Each block refines the representation, adding more and more contextual understanding. Finally, we came to the actual pre-training and generation process, covered in Chapter 5. All this complex architecture is trained on a ridiculously simple task: next word prediction. The model is fed a massive amount of text from the internet, and for every sequence of word, its only job is to predict the very next word. The loss is a measure of how wrong its prediction was. Through backpropagation, the model slowly adjusts its millions of parameters to get better and better at this one simple task. The incredible part, which the book calls an emergent behavior, is that by getting very good at predicting the next word on a diverse dataset, the model learns grammar, facts, reasoning, and even translation capabilities without being explicitly taught them. When it's time to generate text, we give the model a starting prompt, like "every effort moves you." The model calculates the probabilities for every possible next word in its vocabulary. In the simplest method, called greedy decoding, It just picks the word with the highest probability. But to get more creative and less repetitive text, we can use techniques like temperature scaling. A higher temperature makes the probability distribution flatter, giving less likely words a higher chance of being picked, introducing randomness and creativity. Top K sampling further refines this by telling the model to only consider the K most likely words, preventing it from picking completely nonsensical options. Nonsensical options? I don't actually know that word. This is LLM robots make their things. So, what does all of this mean from a developer's perspective? How does building this change the way I think? First, it completely demystifies the API. When I now adjust a parameter like temperature in OpenAI's playground, I have a crystal clear mental model of what's happening. I know it's scaling the logit values before the softmax function, which directly impacts the probability distribution that the multinomial sampling function uses. I know that we are having a lot of terms here, guys. Don't worry about it, for real. Don't focus on it that much. Just focus on the main theme. I'm not just moving a slider. I am picturing the math, and I can better predict its effects. Second, it gives me a profound appreciation for the architecture. Raschka's approach of starting with a dummy GPT model placeholder is exactly how a developer would approach a complex project. You build the skeleton, the interfaces, and then you implement the real components one by one. The layer norm, the feed-forward network, and the transformer block. Seeing the model built this way, with clear modular classes like multi-hat attention, makes the architecture tangible. It's not a monolith. It's a system of interacting components. I could see myself taking the GPT model class from this book and swapping out the attention mechanism with a different one to experiment. That's a powerful feeling. The book is filled with code, but you don't need to read it line by line to get the point. For example, the load weights into GPT function is a complex piece of code that maps the weights from OpenAI saved format into the custom GPT model class we have built. The essence of this isn't the code itself, but the strategy. It shows that the underlying architecture is standardized enough that with some careful mapping, you can load professionally trained parameters into your own from scratch implementation. This bridges the gap between educational understanding and real-world application. Critically though, the book also highlights the limitations. The entire training process we do in the book is on a tiny short story, The Verdict. The model quickly overfits and starts memorizing the text. This is a hands-on lesson in one of the biggest challenges of AI. It underscores why real models like GPT-3 are trained on trillions of tokens. The book even qualifies this, mentioning that training a model like Llama 2 costs hundreds of thousands of dollars in cloud computing. This provides a healthy dose of reality. Building a toy model is achievable on a laptop. Building a state-of-the-art one is a monumental engineering and financial undertaking. The book wisely focuses on GPT-2's architecture because its weights are openly available, making it the perfect subject for this kind of deep dive learning and experimentation. So, as we come to the end of this show, what are the biggest takeaways from Sebastian Raschka's build a large language model from scratch? First, the magic of LLM is built on a stack of surprisingly understandable and elegant ideas. It's not one giant monolithic mystery. It's layers of concepts. Tokenization, embeddings, attention, feed-forward networks, each solving a specific problem, all assembled into a coherent whole. Second, the core of the modern LLM, the transformer, is powered by the attention mechanism. This ability for the model to weight the importance of different parts of the input for any given token is the breakthrough that allowed these models to handle long-range dependencies in language, and become so powerful. Third, the entire complex architecture is trained on a very simple objective: predict the next world. The fact that sophisticated behaviors like reasoning and grammar emerge from this simple task on a massive data set is one of the most profound and astonishing findings in modern AI. And finally, the most important takeaways is the book's central thesis itself. You do not truly understand the system until you have built it. Reading about it is one thing, using it another. But implementing it from the ground up gives you an intuition and depth of knowledge that is simply irreplaceable. The book proves that building an LLM is not an impossible task, reversed for a handful of giant corporations. The core logic, the architecture, is something you can code on your own laptop. It challenges you to stop being just a consumer of AI and become a creator, an understander. So my challenge to you this week is this: the next time you use ChatGPT or any other LLM, don't just see the magic. Try to see the machinery behind this. Picture the tokens, the query and key vectors flying around in the attention mechanism. The transformer blocks stacked one on top of the other, all working to predict that one next word. Because once you have seen the blueprint, you can never look at the building the same way again. Thank you for tuning in to Beep Beep Boop Boop. I have been your host, Baris. Until next time, keep digging under the hood.